Welcome to the next class. Last time we were looking at a process, a very simple process which consisted of a CSTR cooled CSTR, A and B going into the CSTR, reacting to form C. Reaction occurs in the liquid phase. Reactor effluent, which is an ABC mixture, is sent to a distillation column where the unreacted reactants are recovered at the top because they are light and recycled, and from the bottoms you withdraw product C, right, and this is AB recycle, RCY means recycle, okay. And we saw that the steady state operating degrees of freedom for the process is what? 6. And then we decided to put in place a simple minded control system where what we do is flow control the 2 fresh feeds, temperature control the reactor so that the reactor temperature is fixed, all right. Now we need to control the level of the CSTR, which is done this way. We need to control the level of the condenser, which is done this way. We need to control the pressure of the column, which is done this way by adjusting the cooling duty. We need to control the level of the bottom, column bottom, which is done this way. The amount of steam flowing in is set by the operator. The amount of reflux is also set by the operator, okay. So what are the 6 degrees of freedom for this control system? Operator sets this, operator sets this, operator sets the temperature set point, operator sets the reflux, operator sets the reboil or the steam to the column, and these are the 6. Also the level, the level at which you are operating the reactor, 80%, 10%, 20%, whatever, okay. These 6 set points are your steady state degrees of freedom for this control system, okay. Of course there is a set point associated with this, there is a set point associated with this, there is a set point associated with this, but these 2 set points, the level set points, do not affect the steady state. Also the pressure is fixed because you want to operate at whatever is the design pressure of the column, okay. So these 3 in green are not really steady state degrees of freedom, the red are the steady state degrees of freedom, okay. Now when you are running it like this, we discussed last time, even if you see 1 mole of A reacts with 1 mole of B to give 1 mole of C. So if you look at the plant as, if you look at this overall plant boundary, now this goes back to material and energy balances, okay. If you look at the overall plant boundary, if you want to take out only pure C, or let us say 99.9% pure C, what that means is, if you are putting in 1 mole of A, you have to essentially put in 1 mole of B. If you are not putting 1 mole of B exactly, then what that means is either there is an excess of B being put in or there is an excess of A that is being put in, right. Since you cannot let that drop out the bottoms, that excess is bound to build up in the recycle loop. Does that make sense to you or not? Okay, once that makes sense, now let us say we are operating the plant forget the yellow boundary. So let us say we are, I rubbed the recycle off. Let us say the operator decides this is the way, these are the set points that I am going to set. Operator understands that you have to put in 1 mole of A, 1 mole of B. Let us say you got a really dumb operator. What does the dumb guy say? He says, okay, let us put in some moles of A and some moles of B, okay, not necessarily equal. So the two set points are not equal. We are going to build up operation from the dumb guy to the smart guy, okay, so that you understand how degrees of freedom are very important. So you are putting in some amount of A, some amount of fresh B, not necessarily equal. That being the case, what will happen to the purity here at the bottoms? Whatever is excess has to find a way out, right. So if you have, okay, so if you have set the steam at some value, okay, you are getting the excess, whatever is excess coming out, okay. Management says, well, this is only 95% pure, we want 99.9% pure, we do not like this, please operate your process so that we get 99.9% pure product, okay. What does the operator do? He looks at the process, figures out, well, there is too much A dropping down the bottoms, let us say. So what does he do? He increases the steam. Then he gets irritated every time I have to look at the quality and change the steam. So he gets a little smart and he says, well, I will put in a temperature controller that sets this set point. Because the management was not happy with what he was producing, its quality was not good, okay. Once he does this, what happens is, because you are putting in excess amount of B or A, whatever be the case, which was dropping down the bottoms, now the temperature controller does not allow it to drop down the bottoms, yeah. So what will happen to the steam? You have excess of A being put in, that is, the temperature controller is not allowing that excess A to drop down the bottoms. What is the controller doing? It is essentially increasing the steam, yeah. There will definitely come a stage where you cannot increase the steam anymore, okay. So let us say then the temperature controller has been increasing the steam, or maybe the column gets flooded because you are boiling up so much. Your boil up is increasing, now the liquid cannot drop down, the column is flooded, okay. Either ways, what will happen is, you will hit a constraint, or before you hit the constraint, or maybe if the steam goes to maximum, you cannot increase the steam anymore, and now the A which was being sent up cannot be sent up because you cannot increase the boil up anymore, and therefore A starts contaminating your product again, right. What is the problem? The problem is, this control system is not respecting the overall material balance for the process. Overall material balance dictates that A should be equal to B. Is A equal to B? No, you are setting it independently. It cannot be set independently, right. So you need to do something to ensure that A or B does not build up in the recycle loop, okay. The operator then finally understands this, and then what does he do? He says, okay, we will control some composition inside the recycle loop. So let us say he controls a composition inside the reactor of, let us say, maybe A, and to hold this constant, what he does is, he sets the fresh amount of A being sent in, okay. Now tell me, is the overall material balance being respected with this control system in place, or will we still have some problem? Is the question clear? Do not struggle too much, this will work, okay, because if too much B is building up, A composition will go down, you will reduce the A, then A will match B, okay. If A is building up, A composition will go up, you will reduce the A, ultimately it will again match B, yeah. So now we have got again 6 set points. What are those 6 set points? 1, the fresh B flow rate, reactor temperature, composition of A inside the reactor, stripping tray temperature, reflux to the column, and level of the reactor. These are still 6 set points. It is just that the variables that are being specified are different. Earlier we were specifying FA, FB, temperature, level, steam and reflux. Now we are specifying FB, composition inside the reactor, reactor temperature, reactor level, column temperature and reflux. You see what you are specifying, the 6 specifications for the process have changed. With these sets of specifications, your overall control system is respecting overall material balance. The composition controller here will ensure that the A and B fresh feeds are stoichiometrically balanced. This is dictated by the stoichiometry of the reaction, okay. Alright. Now how do we choose, what do we do with these 6 set points? What should the temperature set point be in the column? How do I choose this set point, column temperature set point? It has to be chosen so that the product is 99.9% pure. So product purity specification basically fixes this. So I know how to fix this, yeah, okay. What should my level set point in the reactor be?
Maximum allowable.
Maximum allowable. Why?
Maximum resistance time, more reaction.
So conversion is more, so what? I mean you have to keep answering so what until, so, huh?
More easy. Technically it will be.
Why? That is the question. Why is it economically better to run the reactor at highest possible conversion?
Lesser conversion would mean more of A and B coming to the getting removed in the bottom.
Yeah, so you will require to put in more steam to send the A and B up. In the column, he is saying economics would be better. You need to further quantify that. Why is the economics better? Because if you have more unreacted A and B coming out of the reactor, you need to send it up. That means you need to put in more steam in the column. Yes or no? So your steam consumption per kg product produced goes up if you are operating at a lower level. So you would operate the level at max. Yeah, the set point to the level controller for the CSTR would be what? Max. So I know how to set the level. What about temperature? Let us say there are no side reactions, very simple case, no side reactions. How would you set the temperature? Any value? Design value? Well, I had said that what happens to the conversion if temperature goes up? Increases, so your boiler load will again go down. But can you keep on increasing the temperature in an unbounded way? No. For example, your liquid may not remain liquid, everything vaporizes. So there will be some limit on the temperature, or maybe your catalyst starts to get coked and so on and so forth. Some process constraint will limit what is the maximum temperature at which you can operate this process. That max is where I operate it at. Yeah? ठीक है कि नहीं? Okay. How do I choose the composition set point? There is a CCA, no? There is this set point, composition of A inside the reactor. I can choose this set point to be whatever, It could be too much of A, very little B. It could be too much of B, very little A. It could also be A and B are comparable. Why comparable? Huh? No, it's not so clear to me.
We want A and B to be in the same ratio in the field.
No, I don't think you've understood material and energy balances. Whether the set point is 10% A or 90% A, if this loop is on, A and B, fresh A and fresh B will be stoichiometric. You can choose this composition set point to be 10 mole percent A, you can choose it to be 90 mole percent A, okay. No matter what you choose it at, as long as you are maintaining the composition, fresh A and fresh B will be balanced stoichiometrically. You can think of it this way. If let's say A and B are initially balanced, okay, exactly 100 kilomoles per hour, okay, I give A a pulse of some duration. So B is fixed at 100, A went from 100 to 110 for let us say 1 hour, okay. That extra 10 kilomoles an hour did not drop out. Where did it go? It went into the recycle, okay. Therefore, that extra A has built in the reactor, and the reactor composition has gone from let us say 10% A to 40% A, okay. But after the pulse has been withdrawn, the two feeds are still stoichiometrically balanced. So you can operate it at 40% A, 10% A, similarly 90% A. As long as the composition controller is on, stoichiometric balancing of the two fresh feeds will occur automatically. Does that make sense or no? So my question is, what should I choose it at? Should I run it at 10%? Should I run it at 90%? Should I run it at maybe 40%?
Some reactions,
Reaction is only A plus B goes to C, there is no side reaction.
in some reaction the rate of reaction is higher if the ratio is supposed to
Okay, so let us say the rate of reaction is, thinking is on the right lines. Rate of reaction is equal to K times XA XB. You know, it is an elementary reaction. Let us say this is the rate of reaction expression. By maximizing the temperature, I have set this at max. What should I set XA mole fraction, which is what the composition controller is trying to achieve? When will I get maximum?
When XB and XA are equal.
But if you see, if you plot rate of reaction versus XA, it will look something like this, you know, 50% or whatever, it will look something like this, right. You really cannot operate here because you can operate slightly below it. The because will become clear to you later on. So maybe you will say, okay, 40%. Why 40%? Because that maximizes my reaction rate, which maximizes consumption, conversion, therefore lesser boil up, lesser energy requirement for recycling the unreacted reactants. Does that make sense or no? Yes or no? So I have got 6 degrees of freedom. The moment I start thinking about the process, there are ways of fixing things to reasonable values, fixing those degrees of freedom to reasonable values. Yes or no? So now I know how to fix this. What is it that is left? The two things that are left are fresh B flow rate and reflux, okay.
So,
Yeah.
So when you said XA is to be 40%,
Yeah.
then you are assuming there are only A and B.
Well, yes, that is true. So maybe what we should be doing is,
Like
just a sec,
C free basis.
just a sec, chill man, chill. Maybe we will control this composition. This will be only A and B, right,
Yes.
with very little C. Now this can be made 45% probably. This will work. Some composition inside the recycle loop. Yeah? Does this make sense or no? Okay. Now that it makes sense, So we know how to set the composition controller set point, we know how to set the temperature set point, we know how to set the column temperature set point, we know how to set the level set point for the reactor. Only thing that is left is what? Reflux. That is the only thing that remains. Well, set reflux to a reasonable value so that too much C does not go up the top. That much sense any operator would have. Sufficient reflux so that C does not go up the top. Yes or no?
So how to know that the C is going at the top?
How to know?
How to know that C is going at the top of the column?
Either you are measuring the composition,
There is no composition.
or you are measuring the temperature. Certainly temperatures are measured. If C is going up the top, temperature in the top section of the column will be higher. Okay. So you know that, okay, temperature of the top section is increasing, too much C is going up the top, let me increase the reflux. Okay. Okay. Particularly the boiler being set by the operator was giving me the problem of having no control over my product purity. Right? If A is too much or B is too much, it's bound, the excess is bound to drop down. To fix that problem, I decided to control the temperature. Yeah. But then what happened, even if there is a slight excess of A and B, the boiler keeps on increasing, and then it hits some limit, and then the excess starts dropping down, and again my product is contaminated. That's also not acceptable, and it's not acceptable because A and B are not being fed in the exact stoichiometric ratio. To maintain that stoichiometric ratio, we put in that composition control. So you are free to choose. Degrees of freedom means any 6 variables can be chosen. You see, number of variables minus number of equations. How many things need to be specified to get a square system of equations? Any 6 can be chosen. But the moment you start thinking of how to run the process so that my production objectives in terms of production, in terms of quality are met, what should be specified, or what variables are used to specify those 6 degrees of freedom, that choice becomes quite limited. Okay. By the way, the only thing that I missed here was, what do I do with B? This set point FB. If you want to increase the production rate, increase the amount of fresh feed being put in. If you want to produce less, decrease the set point here. So this is called the throughput manipulator, TPM. Okay. Now this throughput manipulator may be under level control from an upstream process, in which case it's not in your hands. Okay, an upstream process is setting it. How much should the plant produce? Maybe your management is telling you, in which case the set point here is again fixed. It could be a real degree of freedom where you have the flexibility of choosing what is my optimal throughput. Do you see what I am saying? What is my optimal throughput? So what is your optimal throughput? Maybe is governed by the prices. How expensive is energy? What is the selling price of C? And what is the price that I pay for the raw materials A and B? Do you see what I am saying? So now you optimize what should be my throughput so that my operating profit as per expected market prices today is maximized. That can be done. Okay. Right now, for the sake of simplicity, we are just handling the case where I am told how much B must be processed. Okay. When it is a degree of freedom, I am free to choose this set point so that the amount of profit that my plant makes because of operation is maximized. Okay. We have looked at the case where throughput is not a degree of freedom, it's a disturbance. Either your boss is telling you or an upstream plant is telling you, this is the feed, you must process it. Okay. Does this make sense?
So in trick test we will never go for composition control.
No, in this process you have to.
So but composition control is like
Yeah. So what
very
will happen?
sluggish.
Of course it is sluggish. So what will happen is the operator will look at what is happening to the composition of A at the beginning of the shift and maybe at the end of the shift, because let us say he gets 2 samples from the lab every 4 hours, let us say 8-hour shift. So he looks at what's happening to the composition. If the composition of A is increasing, what would he do? He would decrease the amount of A that is being put in. So it is slow, agreed. Nevertheless, this is the only way of running the process.
Why not the 2 flow controllers initially only with the same value of set point?
Because then it doesn't guarantee. It's like the tank problem. Same thing. I discussed this with you maybe in the first lecture, maybe sometime. You know, you're trying to set 2 independent flows when you can't. Even if you give the 2 set points equal, because of mismatch in sensor noise, sensor bias, either you are putting in more feed than you are taking out, or you are taking out more than you are putting in. Right? If that is happening, the tank level is either increasing or decreasing, and some alarm will get hit, high level tank alarm or low level tank alarm. Right? Same thing is happening in this process too. If you do not put a product purity constraint, specifying A and B independently is okay. Because if you are putting in more A, it can come out the bottoms. If you are putting in more B, it comes out the bottoms. The moment you put in a purity constraint that look, my bottom product has to be 99.9% C, what that means is it changes the nature of the problem fundamentally. What is that fundamental?
The output settings for A and B will be
Basically, whatever you are putting in must get consumed in the reactor. If it is not getting consumed in the reactor, if it is not getting digested or reacted away in the reactor, it can't go down the bottoms. It's going to build up in the recycle loop. So the component inventory is behaving like a level. Right? The mismatch can be very small. Maybe it will take months for the inventory to build up before some constraint gets hit and you start getting contaminated product. So the fundamental thing here was, I think the moment you put a product purity constraint, fixing A and B independently cannot be done. If you did not have a product purity constraint, you could have fixed A and B independently. Whichever was excess would have come down the bottoms. Do you see what I am saying? So what is your production objective? That also fixes what is that set of 6 degrees of freedom which makes sense. If you want 99.9% purity in the bottoms, fixing A and B independently does not make sense. It is guaranteed to violate material balance for the whole plant. You may say, okay, I realize it and I am going to set A and B equal, but in practice it will never be equal, because you don't have a sensor which is guaranteed, which is guaranteeing you,
perfect.
yeah. So that control system is guaranteed to fail. How will it fail? You will essentially fill up the recycle loop with either A or B. That's what you don't want to do. So you measure the A composition inside the recycle loop, someplace, maybe in the reactor, maybe in the column, maybe in the recycle stream, wherever, but someplace, and then you hold it constant. If it's building up, adjust how much A or B you're putting in. Yes or no? Please note that the nature of the problem has changed the moment you put in that product purity constraint, because now you cannot take out, because now all of A and all of B must be reacted away. If it's not getting reacted away, you have some excess that's bound to build up. Does that make sense or no? In the recycle loop. So here the component inventory is behaving like a level. The component inventory is non-self-regulatory. If it is non-self-regulatory, the control system must regulate it. How is that being done? That is being done by that composition controller. Yes or no? Just like in a tank, the level is non-self-regulatory, so you control so you must regulate, the control system must regulate the level, so you put in a level controller. Component inventory is non-self-regulatory, while it must be regulated then, it must be controlled. If your control system is not doing that, you see, you have put in place a control system that is bound to fail, and it is failing because of what? Yeah, so it's essentially violating overall material balance. You are setting things independently which you cannot. Just like in the tank, you are setting two flows, it cannot be done, right? Similarly, for this process, fresh A and fresh B cannot be set independently if you are only taking out C from the process. Do you see what I am saying? So this is this is essentially material balance. So your control system must respect overall material balance. Alright? Okay. That's that. Maybe we should do another example. Okay? Let's do another example. And by the way, the other point that I wanted to make was, so you had 6 degrees of freedom. What are reasonable ways of specifying those 6 degrees of freedom is dictated by the process. Hopefully that's clear to you. Also, what are reasonable values for those 6 degrees of freedom? The moment you bring in economic operation, even that gets taken care of. Reactor level, max. Reactor temperature, max. Column temperature, product purity. 1 degree of freedom goes for throughput, 4. What else is left? Composition, if there is no side reaction, well, it has to be such that A and B are comparable. 5th, the only thing that got left was reflux. Well, I'll just set it to some value so that some reasonable value. Okay? So the moment you start thinking of how do I operate this process well, you are left with nothing essentially. Yes or no? So you started, I have so much degree of freedom. What are the production objectives of the plant? That then tells you that, oh, look, these are reasonable variables to exhaust those degrees of freedom, these are unreasonable variables. Specifying FA and FB together independently is unreasonable. Okay? And so on and so forth. And then the moment you decide, okay, how will I maximize my operating profit? By minimizing energy consumption. How do I minimize energy consumption? By maximizing conversion. How do I maximize conversion? Maximum level, maximum temperature, maximum concentration, or comparable concentration of A and B inside the reactor. Right? That takes care of 3, 4. Purity takes care of 5. Only thing that you are left with then is reflux. ठीक है कि नहीं? So degree of freedom is essentially a fallacious. We think that we are free to do, but then when you start thinking what is the appropriate thing to do, you are not free to do whatever you want. There are things that are appropriate, everything else is inappropriate. So you're not really free. You see what I'm saying? Freedom is actually a very fallacious concept. Right? Not only in control system design, in life also. Okay, so now let's look at a different example, where probably we will not have a composition analyzer. Okay, because the process is such that. So let's say, okay, A plus B goes to C. For some reason, let us say C is intermediate boiling. You see, C is heavier than A but lighter than B. So now you will need 2 columns, right? The process will require 2 columns. Okay. So now let's take 2 columns then. So here is my CSTR. I am putting in A, I am putting in B. Of course, I have some cooling for heat removal. A plus B goes to C. I am not writing it. what comes out is an ABC mixture. That mixture is so let's say we take out the A first and then the B. So we take out the A first. You could have also taken out the B first and then the A, but let's just say for some reason we are doing it this way. Maybe A is toxic, so you want to take it out first. Okay, or it's corrosive, so you want to take it out first so that the downstream corrosion is less, whatever may be the reason. Okay. So this is A recycled. B is the heaviest, so C will go up the top, B will go down the bottoms, and it is also recycled. So how do we recycle it? Ah man, forgive me for some poor drawing, but let's just say, okay, so this is fresh B, this is total A, and this is total B, fresh plus recycle. Yeah, so this is recycle B. Okay, now tell me what's the degree of freedom of this process? Steady state operating degrees of freedom. Alright, so this is the process. Its degrees of steady state operating degrees of freedom is 8. 2 for the fresh feeds, 2 for the reactor, 2 each for the 2 columns. So 4 plus 4, 8. Okay. Again, I want to produce, let us say, 99% pure C or 99.9% pure C. So if you start drawing valves, so there is fresh A, there is fresh B, there is also the cooling duty that you have in the reactor, there is this chap, there is this chap, there are all these chaps which hopefully by now you are familiar. Okay, now we want to put in place a control system for this process. Okay, which respects overall material balance. Okay, that is fundamental. Respecting overall and local material and energy balances, the control system must respect that. In fact, it should be designed to maintain the overall material and energy balances. Alright. So now, one way to do it is, well, let's see. What's the point that I wanted to make? Okay, two things. A is the lightest component. Yeah. If A leaks down the bottoms of the first column, where will it go in the second column? It will go in the product, right? So you have to ensure that A does not leak down the bottom of the first column, because if it does, it is bound to contaminate my product. This is just by the nature of the process. Okay. Alright. So I must have this. Oh man, I should use some other color. What was I using? Black. Red. Ah, well, whatever. This must be there because this prevents A from leaking down the bottoms. Yes or no? This has to be there and it has to be controlled real tight. Okay? Alright. As far as the rest of the stuff is concerned, well, let me just draw what comes to my head and then I'll explain to you whatever the hell I'm doing. Okay? Of course, temperature controller for the reactor, that's pretty straightforward. You will have pressure control level control. Product purity must always be controlled, right? Because you are guaranteeing. So maybe you have a composition controller that sets the reflux. Okay. You have a flow controller on the stream, and you have a level controller that goes like this. Similarly, you have a level controller that goes like this. What else? Now, how do we manage A and B? Okay, let's say you're putting in some amount of reflux here, flow control, level control, and of course pressure control. This is all standard stuff, right? No big deal. How do we manage A and B? Notice that, let us say I'm putting, okay, let's just do what we were doing earlier. I'll flow control the fresh A and I'll flow control the fresh B. Not the total B, but the fresh B. Okay. So what are my 8 set points that I am setting? 1, 2, 3, 4, 5, 6, 7 and 8. Okay, these are the 8 set points for the steady state degrees of freedom for this control structure. Yes or no? Does this suffer from that stoichiometric balancing of fresh feeds problem? Yes, no. Yeah, you are setting the 2 fresh feeds. Reaction stoichiometry is still the same. 1 mole of A reacts with 1 mole of B to give 1 mole of C. Yes or no? And you are setting the 2 fresh feeds independently. So there is a stoichiometric balancing problem. Yeah. Okay. So what? If there is, let's say I am putting in too much A, what will happen? I am putting in some amount of B and I am putting more A, more than necessary A. What will happen? Of course, that is true, but what will happen? How will I know that I am putting in more A? That's the question. How will I know in a tank that I am putting in more than I am taking out? By looking at the level. Previous process, how will I make out whether I am putting in more A or more B? By looking at the composition. In this process, if I am putting more A than B, but steam is being used to control temperature, so there is something fundamentally different here. What is the column number 1 doing? No. What is column number 1 doing? Function. Separating A and BC. Yeah. If I am putting in more A, where will the extra A go? It will go to the top. It will go to the top. Right? So what will happen to the level at the top? It will start building up. Level controller will start then opening the valve of the recycle A stream, and the recycle A flow will increase. Yes or no? If recycle A flow is increasing, total A will increase, because fresh A is fixed. Fresh A is fixed. If that amount of fresh A that I am putting in is more than the amount of fresh B being put in, slowly but surely recycle A stream will go up. Yes or no? Now in this case, the process itself is separating, since it is separating A and B separately. A is, how do I figure out whether A is building up in the process or not? By looking at the recycle flow rate. If that recycle flow rate is going up, I am putting in too much A. If that recycle flow rate is going down, I am putting in too little A. Right? So what do?
We control the flow controller of the fresh feed can be controlled with the
Instead of controlling fresh A,
total.
yeah, recycle A or total A, same thing. Total A because the effect is immediate. Recycle A, it will have to flow through and then come back. You see, if I am controlling total A, the moment I change the A flow rate, total A flow rate changes immediately. If I am doing it like this, now this is a dynamic consideration. This flow rate has gone up, recycle flow rate has gone up. I change the amount of A. Well, this flow will not, the recycle flow rate will not get affected immediately. It will go to the reactor, then the level here will build up, and then this flow. So this will be a very slow loop. Conceptually, this will also work. However, this loop will be very slow. That's because the effect takes a long time to pass through the reactor and then the column. Okay, so this will be a slow loop. I don't like slow loops. If I can help it. Can I help it? Yes. Instead of controlling the recycle flow rate, I control the total flow rate. This loop will be fast. I change the fresh air flow rate, total air flow rate immediately changes. Yes or no? I can do the same thing. What? I can do the same thing this way with the B. Okay? Any one of these two set points can be used as a throughput manipulator. If there are no side reactions, whatever we talked about for the previous case also holds. Temperature should be max, level should be max. This temperature set point, what should it be so that it is governed by the impurity in the C, right? Similarly, this composition set point is again governed by the impurity in the C, and so on and so forth. It's 9:50, 2:53. I think this time I don't want to hold you back too long. But the point is, in this process, are you putting in too much A? The process itself is such that because it is doing an AB separation, A is separated out separately, B is separated out separately. Okay, so you know how much A is there and you know how much B is there. Therefore, you don't need a composition analyzer here. The recycle flows are telling you whether you are putting in too much A or too much B. Yeah, and since just like in the tank case, if there is a mismatch, level builds up, well, control the level. If there is a mismatch, total A increases, well, control the total A and the total B. As simple as that. Okay, we'll continue next time.